Voorn from IZON Science Limited from New Zealand. And he will be telling us about how to precisely measure nanoparticles using tunable resistive pulse sensing. I hope I said that correctly. And otherwise, please go ahead with the details.
Thank you, Stefan. So I really was addressing nanobiological particles as slightly different than synthetics, but there's a bit of both in it. We had this poster, which is a bit controversial, but it wasn't meant to be addressed at Melbourne particularly, but DLS in general. And fake probably is a bit strong, but junk data is what I would normally call it. So our view of life is that the era of DLS is over, and we all should move on. By way of background, it came up yesterday that in Nanomedicine, I forgot the exact number, but it was 450,000 odd publications. And then a different speaker said there was about 80% of those non-reproducible. And my question is, where are all the products from this work? And I can't think of a single industry that would have such appalling figures and still be in business. Electronics, automotive, air industry, I mean, it's quite staggering actually. So DLS, completely unsuitable for nanobiologicals or anything complex. Fine if you've got an industrial monodispersed particle set, but that's very rare and almost never the case. NTA evolved to resolve some of the issues of DLS. It still has resolution and standardization issues, but it clearly is a step away from DLS. Flow cytometry, this is really for biological particles, analyzes the biological data, but it's weak on the measurement of small particles because it can't really easily resolve down below 700 or 800 nanometers unless you go to an awful lot of trouble. A TRPS, which is what my company produces, is very, very precise, repeatable, but it does require some understanding and skill. So it's not just a black box you give to a student. Then they put some samples and do their Facebook page while the data is being generated. You have to actually use it. It's an indirect method for biological content, so you have to go to a bit more trouble to get the biological data out as opposed to flow cytometry, which it comes out automatically because of fluorescence. So we see that TRPS and flow cytometry are likely to become an important combination with the flow cytometry providing the high throughput biological data, and the TRPS is actually being used to calibrate the flow cytometer in the same way that you could use it to calibrate a DLS. So this is an old paper, about 5 years old now, but it does just show that the second one down is a TRPS. That is actually what the sample is. They mix 3 monodispersed sets together. TRPS would normally give that by number as well as percentage. Here they just did it by percentage because none of the other techniques could do it by number. And you can see that the worst of all the techniques is DLS, yet it's the most common. So that top curve really doesn't represent the particle set at all. And if you just had that top curve and you didn't know what generated it, there is an infinite array of solutions that, or problems, I guess, that could have generated that curve. So it's useless from a point of view of analysis. Just moving on quickly to exosomes and extracellular vesicles. So in the field, extracellular vesicles is the preferred term, slightly outside the field, exosomes. They're merely one of a type of naturally occurring what we call nanobiological particles. They're very heterogeneous, which mitigates against DLS. They're dynamic, they're changing quickly, short life, very complex. Highly detailed and valuable information. High interest is particle biomarkers. So a particle biomarker is different than a molecular biomarker, different than a circulating cell. So that requires a different approach. You need to understand the particle properties. They've been proposed as therapeutics in several forms, and quite commonly stem cell therapies now have evolved into stem cell-derived vesicles or stem cell-derived exosomes. And again, similarly to nanomedicines or characterization of a number of drug products, you then need careful characterization to make sure that what you're giving the patient is what you think you're giving them. There's also work being done on exosomes as gene therapy vectors, and then again you need the characteristics of the exosomes, the number, and all that. Particle preparation is very important. If you're harvesting these from either cell cultures or from biological samples like plasma, then you need to have an effective particle preparation. So there's a lot of work being done on PEG-based precipitation kits. ExoQuick is one. They're now considered obsolete in the field because they precipitate but not separate, so you're just getting all the proteins and everything else settling out with the vesicles. Ultracentrifugation is still seen as the gold standard, but increasingly seen as issues with contamination. Same thing, co-precipitation, the time it takes to do it. The mechanical effect on the EVs, 120,000 Gs, is been seen to affect their biological capability, and there's a lack of consistency between users and machines. You just go to a different brand and then you're going to get a different output from the UC, so therefore you can't standardise it. Density gradient, more sophisticated again, even more difficult. Similar issues, but they can separate better than UC. SEX, size exclusion chromatography, base separation has come out in the last couple of years. Very simple, fast, very clean, and it works better with concentrated samples than with cell cultures, but you get around that by concentrating the sample. There's now commercial columns sold in various configurations as a QEV platform. This is the type of separation profile. So on the left you see the vesicles that are captured in the fractions roughly 7, 8, 9, 10, and then the proteins come out later, so you get this very, very pure sample of vesicles coming out and totally separated, and it takes 15 minutes rather than 2 hours. So for the exosome field, it used to be a real drama to try and capture and analyse the exosomes. Now it's simple. So with SEC and TRPS, it takes about 30 to 45 minutes, very accurate, highly repeatable. UC itself takes about 2 hours, and density gradient even longer. And you need standardisation for both the diagnostics field and the therapeutic field. So this is a solution that provides that. Different groups doing their work on different instruments, getting different numbers is unhelpful in terms of progressing the field. So this is just the QEV as a product. This is the Nano, which you've probably seen already, so they're the combination. This is an important part where you get quality assurance through calibration. So if you're measuring with TRPS, every single particle is automatically calibrated against a known reference standard. And that's, I think, from a point of view of medical validation, is a really key thing. And it means when you go instrument to instrument, you still maintain an accuracy per particle of about 1 nanometer, because all that you're doing is using the instrument to compare your unknown particle with the reference standard. The way that the data is presented is usually really weak. We were talking about a Z average and a PDI before with somebody. It's actually a really hopeless way to describe particles. You need a two-dimensional plot, and in this case we're just showing that the concentration number is on the y-axis, the size on the x-axis, and if you just define C as a single number, you're going to miss the point, and it doesn't. This is not specific to TRPS, but it's the same for NTA. You're going to miss the point that actually you're not measuring all of the particles. The particles go right down to molecular size and right up to cell size. So your particle concentration has to be defined by its size range. And in this case, we're saying between 70 and 180, there are 8 times 10 to the 9, and there's no size restriction. You go right up. You go to 1.4 times 10 to the 10, and of course below the line where it's I've got the pointer here, there is actually, just because they're not measured, it doesn't mean they're not there. That's just you've reached the sensitivity limit of the instrument. So this is just moving forward to try and educate the field in a better way to describe particles. There was work done on a gold standard for exosomes, so this was based on 6 groups being given the same plasma sample, extracting the exosomes with columns and measuring them, and all that data was collated just to show that standardisation was possible. The CV was about 50 or 60%. The aim is to repeat that and get it down to about 30%, as opposed to a lot of, like for instance, NTA measurements are generally done on a log scale. So 30% is actually quite good. Measurement issues with TRPS and some other techniques. The richness of the particle data is completely different than DLS. So you've got number, size, charge, shape, combinations and applications of all the above. Standardizations for therapeutics and diagnostics is important. New ways to describe the particle data, not Z average and PDI. That's just junk data, I'm sorry. So you need 2D plots, number versus size, number versus charge, charge versus size. This is an example of 4 different particle sizes mixed together. So why do you need field flow fractionation? You can just see these rows here are just the different sizes flowing through in real time. You can just observe that all separated within the instrument, because each particle has a different depth of pulse. So that's all. You just see all that on the software. And this one over here is showing you the velocity of the particles, which you can tune while you're using it. This is about charge, so this is just adding some aptamers to vesicles, so the addition of the aptamers increases the charge. So again, you can use as an identification strategy. This is really part of our charge training tool, so just showing the complexity. You mix different samples together and you can bring out that richness of data. This is some published work where layering DNA on particles, single-stranded DNA, can be bound across like that or like that, and they can tell the difference in electrophoretic mobility even though the charge is the same. So in terms of particle charge, zeta potential, everybody thinks that's charge. It's not, it's something else. It's used in lieu of charge, and it's not really appropriate for nanobiologicals. The whole field doesn't really get that, but they need to. So electrophoretic mobility is what's measured, and the conversion equation is assuming ideal conditions which don't exist with the nanobiologicals. There's a case of drag versus driving force that determines the velocity, the electrophoretic mobility, and you can now measure that drag, and that's reflected in the change of form of DNA, shown that you can do that. Particle-by-particle charge is a really useful tool in EV research and nanomedicine, and that can be used for surface functionalisation, protein corona, a range of other things, QA and comparative data, which I spelled wrong. Standardisation, worldwide need for medical reproducibility means you need to be able to standardise the method. So that starts with sample prep and purification. Set columns are a good solution for that. TRPS is always calibrated and is the same. Thank you.
Thank you. Thank you.
Very quick.
So we realize that this is a highly competitive field, obviously laying a lot of pressure on the analytics departments everywhere involved. And I guess this is a good sign. So we look forward to the future developments. Thank you very much. If there is one question, very urgent, you have Hans right now here, and otherwise at the end. There is one.
Sorry, maybe you have told us and I missed, but do you think this is an analytical technique?
Yes.
Offline? Do you think it could be implemented in line, for example, in systems like microfluidics or?
Yes. TRPS can be implemented in line, and it will be next year. But the Q-Nano as such is more of an R&D tool. So you can do about 50 samples a day, which is actually about the same as you can do with DLS or NTA. They're all similar. So you can do 50 a day, but the instrument requires a user. But an online QA system is on the way. Yep.
Thank you.
Okay, thank you very much. We continue with our third speaker, Clemens Helmbrecht from Particle Metrics.